Hi everyone, this is video number 3 of week 12. In this video, I'm going to go over the first part of the theory of chapter 13. In chapter 13, we have two different topics. The first one, how can we calculate and estimate the stress um, of the thin-walled pressure vessels. The second part is the combined loading, which is basically the unsymmetric bending. And we already talked about this at the end of chapter 11 when we covered the bending stress and how we can come up with the bending stress from the bending moment. We initially started with the symmetrical bending, and then we also covered the unsymmetric bending, which is kind of complicated. So I do not want to cover the theory again, but I'm going to go over another example problems. So in this video, video number 3, I'm going to go over the theory of the cylindrical and the spherical pressure vessel, how we can calculate the stresses. And I'm going to go over the one of the example problem. And the fourth video, the last one for this week, I'm going to go over the example problem for unsymmetric bending. Okay, so let's talk about the pressure vessels. Okay, here I'm going to go to share my screen. Here we go. So here is, by the way, I uploaded this PowerPoint slide on the Blackboard, so you can have it as well. So this is one of the examples in real life. We see this kind of a pressure vessels, and we can store the gas or some other liquid sometimes, and sometimes we have to have an understanding about how we can design this kind of a vessel based on the pressure inside of it, right? And this is one of the example, which is a cylindrical vessel. So this is a cylindrical vessel, and we have two different stresses, one along the length of the cylinder, okay? The other one is the normal stress on this side, okay, along the perimeter of the vessel, okay? So let's say the inner diameter is R and the thickness of this vessel is T, then how can we calculate the stress? So when we make a cut and draw a free body diagram, this is one of the one side of the free body diagram. So we can have this sigma 1, right, along this perimeter of the cylinder, and then we have a pressure from either liquid or gas, whatever material inside of it. So how can we calculate the sigma 1? Sigma 1, this is pretty easy. And by the way, this kind of problem is very popular in the FE exam, but this is very easy, so you can easily get the points. So sigma 1, we can calculate it as the pressure inside of the cylinder times inner radius R divided by the thickness T. So this is the inner diameter, which is 2 times R. So we are going to have this radius here. And this P is a pressure. So pressure is going to be here. And then thickness of your cylinder, of your vessel, that is going to be in the denominator. So that's how we can calculate sigma 1. And then what about sigma 2? Oops. Sigma 2. Okay, so this is the other free body diagram. So we make a cut along the length of the beam, the length of the vessel. So we can think about the pressure this way, and these are those normal stress along the length of this the cylindrical vessel, right? So again, R is going to be the radius, P is the pressure. How can we find out the sigma 2? Again, very simple. So sigma 2 is equal to, earlier it was PR over T, now this is going to be P times R divided by 2T. That easy. Okay, so that's how we can calculate those two different directions of normal stresses. All right, so this is the case for the cylindrical vessel. What about the spherical vessel? This is easy as well. So this is the sphere, right? So we can have this type of the pressure vessel, so we can store the whatever gas or the material inside of it. And we can also think about this, the different direction of the stresses, but because of the shape and because of the geometry, we can easily say that these two normal stresses are going to be identical. Then now that is going to be equal to sigma 2 in the previous discussion. So sigma 2 was P R divided by 2T. So that sigma 2 is going to be the stress inside of the vessel. So with that, we're going to go over the example problem. Really easy, right? Okay. So again, this is the real application of this cylindrical vessel, and this is the real application of the spherical pressure vessel. So here's the problem. This is example problem in your textbook, example 13.1. A cylindrical pressure vessel has an inner diameter of 4 feet and a thickness of 1/2 inch. Determine the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress component exceeds 20 ksi. So in this case, it is not the way we calculate the sigma 1 or sigma 2. Sigma 1 is the longitudinal stress. No, circumferential stress, and sigma 2 is going to be the sigma 1 is a circumferential, and sigma 2 is a longitudinal because that's along the length of the cylinder, right? So in this case, we have a given limit of those sigma 1 and 2. So we'd like to find out what is going to be the maximum internal pressure P. So we're going to kind of back calculate P from sigma 1, sigma 2 equations with a given information of diameter and the thickness. So that's the first part of this question. The second part is, under the same conditions, what is the maximum internal pressure that a similar size spherical vessel can sustain? All right, so look at the first part first. So use the pen option. Okay, here we go. So let's say this is a cylindrical pressure vessel. So we have sigma 1, which was P times R over T, and this was the circumferential stress, and sigma 2 was PR over 2T. And we all know that this sigma 1, sigma 2, this is sigma 1, right? So this is sigma 1, and longitudinal stress is going to be sigma 2. What do you think? Which one is going to be larger with a given pressure and radius and thickness? This is going to be twice larger than sigma 2, right? So we're going to come up with this sigma 1, then that is going to be equal to 20 ksi. So let's just fix that, the sigma 1, which is 20 ksi, that is equal to a known pressure P, and we have the radius, which is in terms of inches, because we are using KSI unit here. So the length was, the diameter, inner diameter was 4 feet. So inner radius is going to be 2 feet. When I convert it into inches, it's going to be 24 inches. So it's going to be 24 here. And then the thickness was given as 1/2, so 0.5 here. And when you calculate this P, it will be equal to 20 times 0.5 divided by 24, right? So it's going to be 417. So 10 divided by 24. So when I convert it into PSI, so multiply by 1,000, it will be equal to 417 in PSI. So that is going to be the maximum, the stress that this cylindrical vessel can sustain with this given information. Okay, and now the second part of the question. Under the same condition, what is the maximum internal pressure that a similar sized spherical vessel? So that means we are going to keep using the same, the inner diameter, which is 4 feet, right? And sigma 2 for this spherical vessel was equal to PR over 2T. So we're going to use this equation. Now the corresponding sigma is now same as 20 KSI is equal to unknown pressure P, and R still the same, 24 inches. And we have 2 times the thickness, which is 0.5. So when you solve it for P, you can easily imagine that it's going to be this multiplied by 2, which is 833 in this case, PSI. This is a rounding error between 417 and 833. So that's how we can get the answer for this example 13.1. So I'm going to stop here and then continue to talk about the other example problem, example 13.2 in the fourth video clip. All right, thank you.